Hello.
Yes, sir. Yes, sir.
Yes, sir.
Okay. So yeah, last class I was discussing four noded isoparametric shear deformable plate bending element. So yeah, now in this we had of course discussed all the theory and everything related to it. So finally we said that the element level governing equation is KED is equal to F external plus F internal, and then K was defined as integration from -1 to +1 with respect to xi and eta. So then what we do is, rather than explicitly evaluating the integrals, we use what is known as Gauss quadrature numerical integration. So the integrals are evaluated numerically, and for that purpose, if you look at this Ke, which was in the last class was defined integration from -1 to +1. Then we had B transpose D into B into determinant of Jacobian matrix d psi d eta, plus we had integration -1 to +1 -1 to +1 Bs transpose into E.
Sir,
So essentially, no, of course, we need to choose how many point m. Yeah, what to do of it. So I will explain you how to get that. And so this is one part, and the other is the you have this shear stiffness term. This term. So this is also replaced by double summation. So double summation is again say I going from 1 to, for shear I am using different number of terms, j going from 1 to ms, and then bs transpose into e into bs into determinant of j. This is evaluated at xi I eta j and wi wj. So now the integrations are performed, are replaced by summation sign, and then the summation is done like this. Now here you would wonder what is M. So M is the number of Gauss points to evaluate bending stiffness terms, because we are using M over here and M over here. So M is the number of Gauss points to evaluate. So that part is involving curvature. Now this B is coming from curvature. So we call that as bending to evaluate bending stiffness terms. And ms is the number of gas points to evaluate transverse shear stiffness terms. Yeah. So
Sir, I have a question.
yeah, yeah.
Sir,
Tell me.
in the assignment for the incomplete element,
Yeah.
uh, we cannot integrate. It is like -1 to 1, and we can also use Jacobian matrix. So how will
In
perform
that
that?
element, in that you see that formulation is different. No, now the assignment what you are talking about is the classical plate bending element, and in that the formulation was done using physical coordinates.
Yes, sir.
So
Then how?
there in the MATLAB you can do the integrations explicitly.
So we'll use the integration function of the MATLAB.
Yeah. You can use that integration function in the MATLAB. Although that integration can also be done numerically also, but then you have to write now the integration because it would be 0 to A, 0 to B. The let us say the element size is A and B,
Yes,
so
sir.
it has to be this this integration no 0 to A, 0 to B. So x and y values can be written in terms of xi and eta, and then you can convert that no you can write that integration also numerically also, but I expect you to evaluate in the MATLAB itself using the integration command.
Thank you, sir.
This I am talking about the this four noded isoparametrics of shear deformable plate bending element based on first order shear deformation theory, for which we have done the formulation in the natural coordinate space, and for that I am writing no that you can do the integration like this. So yeah, no, these are M and S. So now the question arises: how do we define? No, this means that this whole quantity is evaluated at xi and eta j. Similarly, this whole quantity is evaluated at xi and eta j, and then multiplied by wi wj. So and this can be evaluated numerically, but then question arises: how do we choose M and MS? So see, in the Gauss quadrature numerical integration, we need to see the what is the highest power of xi and eta in the integrand. So now if you look at, let us say we take a case that element is a rectangle in the physical coordinate space. So see this B involves del ni by del zeta and del ni by del eta, and this is a four noded element, so say functions are linear in xi and eta. So when you differentiate with respect to xi, it would be linear in eta, and the derivative of shape function with respect to eta would be linear in xi. So you can say this b ultimately would be linear in xi and linear in eta, and d is constant, and then you when you multiply again the b, which is again linear in xi and linear in eta. So the highest power of xi and eta in this integrand would be xi square and eta square. For a element which is rectangle in the physical coordinate space, j would be constant, it would be independent of j. So the highest power of integrand in the expressions for in the integrand are going to be xi square and eta square. So how do we choose this Gauss point number of Gauss points? So m is taken as whatever is the highest power of xi or eta in the integrand plus 1 divided by 2. So in this case, the highest power is 2 plus 1 divided by 2, and then this is approximated to next integer. So m will be taken as 2, and similarly ms in the bs also the highest power of xi and eta is going to be 1, and when you multiply bs transpose E into bs into j, it would be highest power of xi and eta is going to be 2, So you will have again ms will also be 2 plus 1 divided by 2, which is equal to 2. So that means now for this case, for the 4 noded isoparametric element, these terms would be actually the summation of 4 values at 4 points. 4, because 2 along the xi and 2 along the eta direction will give you 4 points.
Sir, this Jacobian will also be a function of xi and eta.
These two by two integration, because 2 along xi, 2 along eta, so it's a 2 by 2 integration. So total 4 points. So this is minus 1 upon root 3 minus 1 upon root 3, and this integration point is 1 upon
Hello, sir.
root 3 minus 1 upon root 3. Yes.
Sir, actually, you were not audible and the screen was not visible. So, could you please repeat this last portion?
Is it visible now?
Yes, sir. Now it is visible.
Yeah, so
But
there might have been some
Sir,
problem your side
two,
actually.
sir,
no,
two
sir.
three
Actually,
minutes
the
it is
whole
back
class
No,
was.
sir.
audible.
No, sir.
Yeah, so I will repeat. So you are saying this, how do we decide M and MS? Is that what you missed?
Sir, actually, M
Hello?
and MS was clear, but someone asked
Sir,
the
after
question that.
MNMS.
So yeah, there was a question that J will also be function of xi and eta. So I said that if you check for the the element as a rectangle in the physical coordinate space, if the element is a rectangle in the xy coordinate space, so then J will be constant. So determinant J would be constant, and then B are basically B transpose or B and BS, they are only linear functions of xi and eta. So when we multiply B transpose and B, we will have highest power of xi and eta as 2. So that is what that highest power of xi or eta plus 1 divided by 2 approximated to next integer gives you the number of Gauss points. So that is what I explained. But if say the element is not a rectangle in the physical coordinate space, that is xy coordinate space, in that case J will be also function of xi and eta. But I said we still use 2 points because we have this M actually as 1.5. So yeah, since we are using a higher number, so it accounts for the J being function of xi and eta. So that is also, of course, if the element is too much distorted from a rectangle, then it may not work. Then you might have to use a higher number of Gauss points. But if the element is slightly distorted, your 2 by 2 integration still works well. So that is what I explained. So then I was talking about the integration point. So it is a 2 integration along xi and 2 along eta. So it's a 2 by 2 integration. So there would be 4 Gauss points. So this is first Gauss point is minus 1 upon root 3, minus 1 upon root 3, and then 1 upon root 3 minus 1 upon root 3, and this will be minus 1 upon root 3 plus 1 upon root 3, and this Gauss point would be 1 upon root 3, 1 upon root 3. So these are the values of xi and eta at gas points, and values of w for 2 by 2 integration when we have 2 points along xi and eta direction. So then w1 and w2, because I and j are going to range from 1 to 2, so w1 would be 1 and w2 will also be equal to 1 for 2 by 2 integration points. So this means that you have to evaluate, see how you do actually is no at each gas point you start with the, let us say, this gas point. So evaluate your shape functions, derivatives of the shape function, Jacobian and everything at this point, then calculate b at that point multiplied by w1 and w1, then plus add, then evaluate this whole quantity at second gas point at this gas point and add to the previous one, then evaluate it at third gas point, that is this gas point, and add it to the previous value, and then again calculate b transpose d bj wi wj at fourth gas point and add it to the previous value. So when you add the contribution from all the 4 gas points, you get your stiffness matrix. So that is how the stiffness matrix is evaluated. So if you are writing a code, you have to do it in that sequence, that you have a outer loop for number of gas points along xi direction, then the loop along number of gas points along j direction, then call a subroutine which calculates shape functions and their derivatives with respect to xy, Jacobian, etc., and then call a subroutine which calculates b, and then multiply b transpose bj wi wj and add to the previous value, and then when that loop completes I loop and j loop, you get the stiffness matrix for the element. So that is how it is actually done. So then
Power of
Simi,
sir, the power of xi and eta will always be same.
see, if the element is a rectangle in the physical coordinate space, then for all the elements it is going to be same. But if element is not a rectangle in the physical coordinate space, so if there may be a slight deviation, so the power of xi and eta may actually increase. So that is accounted for in this, because we are using 2 integration points along xi and eta, whereas we actually require 1.5 as per this rule. So we are already approximating to 2. So that also works. But if the element is too much deviated from a rectangle, then yeah, you will have to use higher number of gas points, maybe 3 or 4 gas points,
No, sir.
because
Actually, I am asking.
power of xi and eta would increase.
Sir, actually, I am asking the m, the summation m for xi and for eta will be same or can be different. The power of xi
That's a
and the
xi
power of
and eta. Yeah, no, yeah, they will be same. Xi and eta powers are usually will be same.
okay, sir. Okay, thank you.
So that is why we are using same number. So even if, let us say, the power of xi is more and eta is less, even then we use the number of points which is equal to the highest of the two.
Okay, sir.
Yeah. So we use same number of gas points along xi and eta directions. So yeah, this is numerical integration. So then same way now you have this f external for the element. So the f external for the element was integration from -1 to +1, integration from -1 to +1, and then we had hw transpose into q into determinant of j into d xi d eta. So this is also converted into double summation, and the number of integration points will be equal to, say, I'm
Hello, sir.
Hello. Hello, sir.
Sir, you are not audible.
Yes, he also freeze.
You have to write, I think, in the comment section.
equal to a by 2 plus a by 2 into 1 minus 1 plus xi.
Sir,
So this is the relationship between xi
sir,
and x.
sir,
Yeah,
your screen again froze just when you
pardon,
wrote the expression. Your screen
pardon.
again froze. Your screen again froze when you started doing expression for f external.
If
You
our
were not audible. From the f
but
external part, you were not audible.
my side there is no. But is it visible now?
Yes, sir, it is visible now.
But my side there is no problem. I think some problem may be there in your side actually.
No, no,
So
sir.
see,
Actually, you
anyway,
were
I'll
not.
repeat. So the f external is the integration from -1 to +1 along the xi in eta direction HW transpose Q into J d xi d eta. So this is also converted into a double summation, I going from 1 to m and j going from 1 to m, HW transpose Q into J evaluated at xi I eta j and into Wi Wj. So this is how you do this. So this is similar to what we do for the stiffness matrix. Then I was telling that suppose if you want to use this Gauss quadrature numerical integration, where the integration is not from -1 to +1, but say it is from 0 to a and 0 to b, then fxy dx dy is converted into a double summation, I going from 1 to m, j going from 1 to m, fxy evaluated at xy y j and wiwj. Let me put this wiwj as bar so that these are different from w and wi and wj we have discussed earlier. So see, x will be written as a by 2 plus a by 2 into 1 plus xi I. So a lower limit when xi I is -1, xi is -1. So this will be so this will not be plus. Let me correct this. Yeah, you are going to just relate xi and eta. So no, this is going to be plus a by 2 into xi I. So when xi is -1, this is 0, and when xi is +1, this is a, and it's a linear variation. So this is how you calculate. So the already the Gauss points are no, they available in books. If you see Gauss points for different integration, if it is 1 point integration, if it is 2 point integration, if it is 3 point integration. So the values of gas this gas point values of xi at gas points are available. So from that you can calculate xi, and similarly yj yj will be b by 2 plus b by 2 into eta j. So similarly when eta j eta is -1, y will be 0. When eta is +1, it would be b. In between it will vary between 0 to b. So from this you can calculate basically xi and yj, and then wi bar will be equal to now a by 2 into wi, and wj bar will be equal to b by 2 into wj. So like that, no, you can use this Gauss quadrature numerical integration for integration of this type also. If the limits are a1 to a2, b1 to b2, then also you can do. So this a by 2 would be replaced by a1 plus a2 by 2 plus a2 minus a1 by 2 into xi, and similarly b2 b1 plus b2 by 2 plus b2 minus b1 by 2 into eta. That would be your yi, and then w's would be a2 minus a1 by 2 into wi, and wj bar would be b2 minus b1 by 2 into wj. So that way also you can do these integrations. So you can use Gauss quadrature numerical integration to evaluate the integrals of this type also. So this is so now what we discussed is the no, 4-noded isoparametric element. Then no, similarly you can formulate the 8-noded, 9-noded isoparametric elements also. So now suppose no, I will just briefly tell you about this 8-noded isoparametric element. So now in this case, what we do is this is isoparametric elements in the physical coordinate space. The element can be a simple rectangle, or it can be arbitrary quadrilateral, or the element can have curved boundaries. So all that is possible. Now the element can have curved boundaries also. So let me sketch the element. So this is x and this is y, and the element is, let us say, it can be, as I said, yeah, in actual situation the element can be a rectangle, it can be a quadrilateral, it can have curved boundaries. So these are the nodes, eight noded element we are talking about. So this is corner node 1. Then first we number locally, first we number the corner nodes. So 1 2 3 4, and then the mid side nodes, so 5 6 7 and 8. And these nodes are located at the the mid side, the intermediate nodes are located at midpoints. First we are numbering locally corner nodes, and then the we are numbering the mid side nodes. This is mapped to a square in the natural coordinate space. So that means, let us say we have xi and eta, the corner nodes, and then the mid side nodes. So these are the corner nodes 1 2 3 and 4, and then the mid side nodes 5 6 7 and 8. So this is what the 8 noded element be. And we will have the primary variables, that is w, theta x and theta y, as degrees of freedom at these nodes. So all the nodes will have w1, theta x1, theta y1 as degrees of freedom. And node 1 is corresponding to node 1 here in the natural coordinate space, similarly 2 3 up to 8. So now in this case, because at each node we have 3 degrees of freedom and total 8 nodes, so corresponding to each variable, that is w, we will have 8 degrees of freedom in the element corresponding to theta x 8, and similarly corresponding to theta y 8. So we will choose the approximate solution within the element for all the variables w, theta x, theta y, and also x and y, using this eight terms in the polynomial. So it would be a0 plus a1 xi plus a2 eta plus a3 xi square plus a4 xi eta plus a5 eta square plus a6 xi square eta and plus a7 xi eta square. So these are the terms we will choose, and then now you express a0 a1 up to a7, all these constants, in terms of w1 w2 w3 up to w8, and then put them back here, and then when you collect the coefficients of w1 w2 w3, you get the shape functions. So from this you can see the procedure we have already discussed. You can write this w as summation I going from 1 to 8 ni wi. So similarly, same way you can do for theta x. Theta x would be I going from 1 to 8 ni theta xi. Theta y will be equal to summation I going from 1 to 8 ni theta yi, where no theta wi, theta xi and theta y are the values of w, theta x and theta y at node I. So similarly, you write the x and y coordinates also have to be written in terms of xi and eta. So x you write as summation I going from 1 to 8 ni xi, and y is equal to summation I going from 1 to 8 ni yi. Only difference in these two set of interpolation, that is the field variables and the coordinate geometry, is that the wi, theta xi and theta yi are unknown, whereas xi and y are known values of the x and y coordinates of node ith node. So now for this, when you look at the shape functions, so rest of the steps are same. The way we formulated 4-noded isoparametric element, in a similar manner you formulate the 8-noded isoparametric element. So I will not discuss all the steps, you can do that. When you look at the shape function, so if I want to write n1, so n1 is equal to, now n1 is the shape function corresponding to this node. So what we can know, there is a direct way of writing the shape function. So n1 should be unity at 1 and 0 at rest of the nodes. So for that we can take the equation of this line, we can take the equation of this line, and of course minimum number of lines we need to take. So equation of this line is xi equal to 1, so 1 minus xi, and equation of this line is eta equal to 1, so I can write 1 minus eta. And then no, it has to be 0 in no, along this line 8 and 5. So I take a line along 8 and 5. So that equation of line is xi plus eta equal to minus 1, or 1 plus xi into eta. So the equation of no, this line going from no, 5 to 8 or 8 to 5. So equation of no, this line. And then you have to make sure that it is unity at node 1. So we put xi node 1, xi equal to minus 1, eta equal to minus 1. So this will be actually minus 4, so be divided by minus 1 by be multiplied by minus 1 by 4. So we get n1. Similarly, when we want to write the shape function n2 is corresponding to node 2. So for that we take the equation of this line, equation of this line, an equation of the line joining 5 and 6, that is this. So that would be minus 1, and then we make sure that it is unity at node 2. So we will get that as 1 plus xi, 1 minus eta, and 1 minus xi plus eta. You can look at those lines. So similarly, n3 will be minus 1 by 4, 1 plus xi, 1 plus eta, and 1 minus xi minus eta. And here n3 means xi and eta both are plus 1, so it would be the 1 plus xi into 1 plus eta into 1 minus xi eta would be minus 4, so we divide it by minus 4, so we get the unity, no, the n3 is unity at node 3. So similarly then n4 would be minus 1 upon 4, 1 minus xi, 1 plus eta, and 1 plus xi minus eta. So these are the shape functions corresponding to the corner nodes, and these are also actually known as serendipity shape functions, because the element has got only nodes at its outer boundaries, and if no, we have nodes at the inside also, then that is known as Lagrange element. So say for example 9 noded element would be a Lagrange element. So similarly n5, if you look at, so for n5 you have to take 5 is this node. So for that we need to take the equation of this line, equation of this line, and equation of this line. So 1 plus xi, 1 minus xi, and 1 minus eta. So this will be 1 minus xi, 1 plus xi, and 1 minus eta. Then we have to make sure that it is unity at node 5. So at node 5 xi 0 eta is minus 1, so be divided by 2, so that we get it as unity. So then similarly n6 would be half, and then you have 1 plus xi, and you will have 1 plus eta, 1 minus eta. So for n6 what you are doing is you are taking the equation of this line 1 minus eta, equation of this line is 1 plus eta equal to 0, of course, and so we are taking only that the whatever we have on the left hand side, and equation of this line is 1 plus xi. And then n7 would be half, and n7 is basically again you will have 1 plus xi, 1 minus xi, and you will have 1 plus eta. And then n8 will be half. So n8, when you're looking at n8, is this, it will be equation of this line, equation of this line, and equation of this line. So you will have 1 minus xi, and then 1 plus eta, and 1 minus eta. So at node 8 eta is 0 and xi is minus 1, so when you put that you get 2, so you divide it by 2, so that it is unity. So these are the shape functions for 8 noded isoparametric element n1 to n8. These are the shape functions you can write. And then the element level, no, all the other steps are same. So you will have element level governing equation as Ke into De is equal to F external for the element plus F internal for the element. So this is the element level governing equation, and again know that all these quantities will be evaluated using Gauss quadrature numerical integration. So this will be again summation I going from 1 to m, j going from 1 to m, and then we will have this B transpose into D into B into determinant of Jacobian, whole thing evaluated at xi I eta j wi wj. Now for 8 noded element you would notice that B transpose would be 24 by 3, D is 3 by 3 matrix, and this is 3 by 24. So the stiffness matrix is going to be 24 by 24 for the 8 noded element, whereas for the 4 noded element it was 12 by 12. Plus you have the no, this is the bending stiffness term, and then you have transverse shear stiffness terms. So I going from 1 to ms, j going from 1 to ms, and then you have bs transpose into e into bs into determinant of the Jacobian matrix. Whole thing is evaluated at xi I eta j into wi wj. You will see that Bs transpose would be 24 by 2, E is 2 by 2, and this is 2 by 24. So this is also no same thing, 24 by 24 matrix. And f external of course will be f external for the element, that would be summation say I going from 1 to m, j going from 1 to m, and then we will have hw transpose into q into determinant of j evaluated at xi I eta j into wi wj. So this is how you will evaluate this load vector. Now how do we choose m? So as I said, assuming that element is a rectangle in the physical coordinate space xy coordinate space, so in that case the Jacobian matrix would actually be constant. So now if you see the shape functions n1 to n8, they are in terms of xi square and eta square. So if you differentiate the shape function ni with respect to xi, it would be linear in xi and square in eta. Similarly, when you take the shape function derivative with respect to eta, it would be quadratic in xi and linear in eta. So overall you can say V is going to be quadratic in xi and quadratic in eta. So when you multiply V transpose D into V, it would become xi to the power 4 eta to the power 4. So highest power of xi and eta in the integrand V transpose dBj is going to be 4. So the Gauss point would be 4 plus 1 by 2, and this is approximated to next integer. So we will take 3 points. Similarly for ms also the same logic. So because shape functions are quadratic in xi and eta, so when you do bs transpose into e into bs, it would become xi to the power 4 eta to the power 4. So highest power of xi eta in the integrand is 4. So we take 4 plus 1 by 2 approximated to next integer, so that is 3. So we will use 3 by 3 integration for the 8 noded element. Now so that 3 by 3, the points now you can find out from the books, the locations of the Gauss points and the weight factors. So this is xi and this is eta, and there would be 3 now Gauss points. So when we take one xi and vary along eta, so we will have these 3 Gauss points like this, and then we will have this. These are going to be the Gauss points. So now we will evaluate this B transpose dBj determinant j at 9 points and add all the contributions, and then after adding the contribution from all the 9 Gauss points, we get the stiffness matrix. So these are the 9 Gauss points: 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you will have to do this for the 8 noded element. And yeah, so now see, we talked about shear deformable plate bending element, 4 noded element, 8 noded element. Similarly, you can formulate a 9 noded element. That means having mid side nodes and also the center node. That would be a 9 noded element. So you can formulate that also. You can see how to get the shape functions. So similar logic what I did for the 8 noded, you can from the same logic you can get the shape functions for the 9 noded element. So you can do that. So I'm not discussing that. Now the one of the important thing is knowing the shear deformable plate element. So we have discussed classical plate bending elements. We have discussed first order shear deformable plate theory based elements. Now the problem is, suppose now we use these shear deformable elements for solving the thin plate problems, where no A is much larger than thickness, A by H is greater than say 30, so it would be a thin plate, and there is a problem called shear locking. So although we expect know that the deflection should reach to the whatever is the value we get from the classical plate theory, but instead of that, no, this if you use the fully integrated means they use the number of gas points m and ms as I discussed for evaluating the stiffness matrix. So if you use fully integrated shear deformable plate elements for thin plate problems, it under predicts the deflection, and that under prediction is known as shear locking. So it will happen if you are using this element for thin plate problems. So and of course we would like to use that no, rather than using two different types of element, but then we'll have to take care of this what is known as shear locking. And this is also no in the plasticity and all, you also have the incompressible materials, you also have a phenomena called volumetric locking. So this shear locking I am talking with respect to plate theory, but similar phenomena is there in incompressible material volumetric locking, or in elastoplasticity volumetric locking. So you have to take care of that. So more or less the methods to eliminate this shear locking are similar in the transverse shear locking problems, in the volumetric locking problem. So you will see in the packages many of the elements are there which are reduced integration elements. So the reduced integration is used to eliminate locking problem, either the transverse shear locking or volumetric locking. So I am going to explain here for plates the transverse shear locking. So now for thin plates, so if we are using the the thick plate formulation, that is first order shear deformation theory. But when we use it for thin plates, so for thin plates we will have say this gamma xz and gamma yz will approach to 0. That is, for thin plates normal will remain normal to the deformed middle surface. For thick plates it does not remain normal, but for thin plates it will remain normal. So gamma xz we have defined it to be del w by del x plus theta x, and this will approach to 0. So then you can say that theta x will actually approach to minus del w by del x. So that no, that's the classical Kirchhoff plate theory, where theta x is minus del w by del x and theta y is minus del w by del y. Similarly, gamma yz will also approach to 0, and that will give you theta y approaching to minus del w by del y. So now in this when this is happening, these constants theta x is equal to minus del w by del x and theta y equal to minus del w by del y is getting numerically enforced in the finite element formulation. It leads to a problem. So rather than getting the correct deflections, you will under predict the deflection if you are using fully integrated this shear deformable plate elements. So let me write what this shear locking is. So when shear deformable plate bending elements, let me say fully integrated, so without any reduced integration. So fully integrated, that means we use the number of gas points required to exactly evaluate the integrals. So hence shear deformable fully integrated uh, plate bending elements, that is shear deformable plate bending elements. So plate bending, let me also add shear deformable, so I think that is important. So when shear deformable fully integrated shear deformable plate bending elements are used to model thin plates deflection. So in this case deflection is under predicted, that means lower than what it is exactly there. So this deficiency, this is a numerical deficiency. So this this is a numerical problem, numerical deficiency. This numerical deficiency is referred to as transverse shear locking. Shear locking. So this is what I explained. Let me explain you the why it happens like this. So let me explain you the reason. Because now the transverse shear part of the stiffness is over predicted, so the stiffness is more, so the deflection is less. So how that happens? So let me take an example of element formulated in the physical coordinate space, just a rectangle, let us say. So this is x and y, and in the physical coordinate space the element is a rectangle. So let us say we have this as a rectangle. The nodes are 1, 2, 3 and 4. So I will explain with respect to this. So four noded element. So let me take four noded element as an example to explain this problem. So in this case it is a four noded formulated in the physical coordinate space. So W would be a0 plus a1x plus a2y plus a3xy, and theta x would be b0 plus b1x plus b2y plus b3xy, and theta y will be c0 plus c1x plus c2y plus c3xy. Now if you look at the expression for gamma xz, the problem is coming from the transverse shear strength. So if you look at the gamma xz, which is del w by del x plus theta x, so this will be equal to del w by del x is going to be a1 plus a3y, and of course I know your theta x is b0 plus b1x plus b2y plus b3xy. So now you can take the similar terms together. So we can say a naught plus b0 is one term, and then we have this b1 into x, and then we have a3 plus b2 into y, and plus we have b3 into xy. So now for thin plates, now if we are using the same element for thin plates, so for thin plates we know that this gamma xz is going to approach to 0 everywhere within the element, and when this is approaching to 0 everywhere within the element, so that means the separately constant term has to approach to 0, term linear in x has to approach to 0, term linear in y has to approach to 0, term bilinear in x and y has to approach to 0. So that will give you the condition that a1 plus b naught is approaching to 0, b1 is approaching to 0, a3 plus b2 is approaching to 0, and b3 is approaching to 0. So now if you see, as far as this first constraint is concerned, a1 plus b naught, without a1 and b naught being individually 0, this summation can be 0. So a1 and b naught are of opposite sign and equal magnitude, so they can approach to 0. Similarly, a3 plus b2 have got contributions from both del w by del x and theta x. So without individually a3 and b2 being 0, this term can be 0. But now this b1 is approaching to 0 and b3 is approaching to 0. So when b1 and b3 is approaching to 0, so this implies that the theta x ultimately is getting enforced because b1 and b3 are 0. So if b1 and b3 are 0, then it would be simply b naught plus b2 into y. Your theta x will approach to that is linear in x and linear in y and constant along x direction. That will be the variation of theta x. That is what is getting enforced when we use the shear deformable plate element for solving thin plate problems. And similarly, if you look at the gamma yz, so gamma yz is del w by del y plus theta y, and this will be no a2 plus a3x when you differentiate, and plus c0 plus c1x plus c2y plus c3xy. So from this you can similarly say that for thin plates, again when we have thin plates, so for thin plates, gamma yz will approach to 0, and that will give you the conditions which will be a2 plus c naught approaching to 0, a3 plus c1 approaching to 0, c2 is approaching to 0, and c3 is approaching to 0. So this implies that theta y is getting enforced as c naught plus c1x. So that is linear along x and constant along y. So this is what happens. Now if we use this element to solve a problem, so let us say now we have discretized a rectangular plate into 4 elements. No, that is no, the whole this element is used to solve a no, this problem. So 4 noded elements. So let us say these are the global nodes. Global node numbers are, let us say, 1 2 3 4 5 and 6 7 8 and 9. So global nodes are these 1 2 3 4 5 6 7 8 9. Locally for the first element, the first node would be 1, second node would be 2, third node would be 5, fourth node would be 4. For element 2, the first local node is 2, second local is 3, third local is 6, and fourth local is 5, like that. And this is 3 and this is 4. So these are the elements. And let us say now the plate is subjected to transverse load, and it is all the edges are fixed. All the this transverse shear locking is also sensitive to boundary conditions. If the boundary conditions are stiff ones, so that is, for example, clamp is a stiff boundary condition, so the locking would be more severe. So now at the boundaries, if you look at, now if I look, let's look at the element 1. So on this boundary, w is going to be 0, theta x is going to be 0, theta y is going to be 0. Similarly, on this boundary, w is 0, theta x is 0, theta y is 0. That's the clamp boundary condition. W, theta x and theta y, all three are 0 on the boundaries. Now if I look at, so now the theta x, we said no, it is theta x, if you look at, we said it is because of the thin plate constraint, theta x is becoming linear in y and constant along x. So now since the theta x along y also, if you look at, so theta x no, is 0 here, 0 here, so then you will find that these two constants, the b naught and b2 will be 0. So you will find that theta x and theta y will be 0 everywhere within the element. For thin plates, theta x will approach to 0, theta y will approach to 0. And once theta x and theta y are approaching to 0, so the deflection w will be under predicted. So this implies that w is also approaching to 0. That means deflection is under predicted. And this is why it is. This is because of the transverse shear locking, as I explained. Yeah. So hello, am I audible?
Yes, sir.
Yes.
Yes, sir.
No, this is the reason why the transverse shear locking happens for when the shear deformable plate element is used for solving thin plate problems. So if the boundary is stiff, the locking would be more. That means we will know the deflection would be under predicted more. And if the boundary conditions are, let's say, some edges are free or simply supported, then the locking would be less, and the locking would be more if the plate is thinner and thinner. So the locking severity is going to be actually more. So now you have to take care of this this phenomena, this problem in locking problems. So similarly, there is a concept of volumetric locking, as I said, for incompressible materials and elastoplasticity. So there also you have to take care of the volumetric locking. So how do we eliminate this shear locking? So there are methods to eliminate shear locking. So I think methods to eliminate shear locking. So one such thing is one most commonly used technique is reduced or selective integration technique. So let me list first all the methods which are available for solving this problem. So one is reduced slash selective integration. See, this problem will not be there if you are using classical plate bending element to solve a thin plate problem. It will not be a problem. The problem is coming when we are using shear deformable plate bending elements for solving thin plate problems, that where the plates are thin. So then only this problem is coming. So one way is to use the reduce or selective integration. So whatever is the full integration to exactly evaluate the stiffness matrices, whatever integration is your number of integration points are required. Rather than using that, we use lesser number of integration points. So we under integrate the stiffness matrix so that no the deflection is predicted properly. So no, there is a reduced integration means both bending and transverse shear stiffness terms are evaluated using reduced integration, and in selective integration the bending stiffness term is evaluated using full integration, but no transverse shear stiffness term is integrated using less number of gas points, reduced integration. And then other is we use what is known as consistent interpolation. Consistent interpolation. In this, what is done is, if you I am going to explain all the three techniques in detail, but I am briefly telling you. So in consistent interpolation, now if you look at the transverse shear strains, the problem is coming because no del w by del x has less terms and theta x has got more terms. Similarly, del w by del y has more terms and theta y had got no del w by del y has less term, and theta y has got more terms. So if we interpolate no theta x and theta y such a way that no del w by del x plus theta x are of the same form, del w by del y and theta y are of the same form, then this locking problem is not there. So that is known as the consistent interpolation. So interpolation of theta x should be similar to del w by del x, and interpolation of theta y should be similar to del w by del y. Then it is known as consistent interpolation. And third approach is known as modified interpolation functions. Modified interpolation, that means only for the purpose of substituting theta x and theta y in the expressions for gamma x and gamma yz, we modify the interpolation of theta x and theta y. So that is known as modified interpolation. This is also known as field consistent approach. So these are the three techniques, and I will be discussing these in details in the subsequent lectures. So I think I want to stop here, and if you want to ask any doubts and questions, you can ask.
Sir, how that theta x and theta y is tending to 0?
Yeah, see, that is what I said, because when plate is thin, so I have talked about that over here. So now if the plate is thin, so we have seen that in thin plates the observation is observation, and also the three-dimensional elasticity solutions depict that when a plate becomes thin, the normal to the deformed middle surface remains normal to the deformed middle surface, and that means theta x, the is going to be del w is going to be minus del w by del x. So I am saying for thin plates gamma xz is approaching to 0, approaching in the sense, no, because absolutely when you have a thin plate it would be exactly 0, and similarly gamma yz would be 0. So that is what I am saying, that if no del w by del x plus theta x, that is what is gamma xz. And if you are solving a problem which is thin plate, and you have got although gamma xz and gamma yz in that, but they should be 0. So for the thin plates, numerically automatically this term will approach to 0 for thin plates. That's the property of thin plates. That is, for thin plates, theta x is minus del w by del x, theta y is minus del w by del y. And so because of that, these are approaching to del w by del x and del w by del y. Then now, so what was your question? Please repeat again.
Sir, how that theta x and theta y is tending to 0 while we are
Yeah,
considering that four
in the
element.
in the yeah, the assembly of four elements you're talking about here. So now we have said that when gamma xz and gamma yz are approaching to 0, so this theta x is b naught plus b2y. So it is linear in y, constant along x, and theta x is constant along x. So now if you see, the boundaries are fixed boundary. So on the boundaries theta x and theta y are 0. Now theta x is linear in y and constant along x. So if it is constant along x, it is 0 here. So it is 0 here theta x, and it is constant. So that constant would be nothing but because it is 0 here, and it will remain 0 throughout along the x direction. Similarly, when you look at theta y is linear in x. And now if you look at that theta y is linear in x. But if you look at 2 points along x, at this point theta y is 0, at this point it is also 0. So the two constants would be 0. So you will find that the theta y will also be 0 throughout along x direction. And similar logic you can extend along y direction. That is, theta x and theta y both would be 0 along y also, because they are 0 on the boundaries, both theta x and theta y. So that is how theta x is a linear in y, constant along x, and that constant value is 0 here, so it would be 0 throughout. And theta y is linear in x, but it is at 2 points along x direction. That is, at this point it is 0, at this point also it is 0. So it would be 0 because those two constants c0 and c1 would be 0, so it would be 0 throughout. So that means any line if you take, it is going to be some places it can be slightly, it can have a non-zero value, but that value would be small. So you it may not be exactly 0 throughout, but it is tending to 0, and that is why the finally w is tending to 0. And if you use more number of elements, then also the locking reduces. And if the boundary conditions are softer boundary conditions, instead of this, if you have simply supported boundary condition, the locking would be less. So this is just an idea to give. I was trying to tell you that how this locking gets enforced and the deflection gets under predicted. So is it clear?
Yes, sir. Thank you.
Yeah. So are there any other questions?
Sir, I have a question. From this logic, we can say that for thin plate, classical plate theory is more suitable than Mendel's plate theory.
Yeah, that is right. But the problem is, see, when we have a complex structure, a complex combination of plates, so then you cannot easily identify whether it is a thin plate or a thick plate, because from the, it depends on the what is the distance between discontinuity to discontinuity, and what is the thickness over there. So it is not easier to identify whether it is a thin plate or thick plate. So we will like to use an element which predicts the results accurately for both thick as well as thin plates. So then we want to have an element which is free from shear locking, and it is also shear deformable. So that is why we are discussing this problem. Yeah, but for thin plates, definitely the classical plate bending elements are better compared to use of shear deformable plate bending elements. But where we
So in
don't know, then we
so
want
in
to use an element which predicts the results for both cases.
so in other words, for thick plate, we can use first order shear deformation theory.
Yeah, for thick plate, you can use first order shear deformation theory. For thin plates, you can use classical plate theory, but I am saying where you can't identify. So part of the system, when it's a combination of multiple plates with different thicknesses, so then it is actually difficult that which portion we should use thick plate, which portion we should use thin plate theory. So then you need to use an element which gives the accurate results for both. So if it is shear, somewhere shear deformation is happening, the element should automatically take care of that. And if somewhere thin plate assumptions are getting enforced, the element should automatically enforce that. So that is why use first order shear deformable plate theories with locking eliminated and the associated problems.
Okay, sir.
Yeah.
Sir,
Yes.
hello.
Yeah.
Sir, can you please explain the consistent interpolation and the methods to eliminate shear locking again?
So I'm going to discuss in detail all these three techniques. So what I was saying is, now this problem is coming, now you have gamma xz del w by del x plus theta x. So del w by del x is linear in y. So the interpolation of theta x should also be similar. It should have a constant term and linear in y. Or other words, if you use 8-noded interpolation for w, so del w by del x would be linear in x, and then theta x interpolation should be linear in x. So that is known as consistent interpolation. I'm going to discuss
Okay,
that
sir.
in detail. In the subsequent classes, I'm going to discuss that.
Okay, sir. Thank you, sir.
Are there any other questions? Anybody? Okay, so if there are no questions, I am stopping. Thank you all for your attention.
Thank you, sir.
Thank you, sir.